Hey everyone, if you're a junior engineer tuning in today, I am so thrilled you're here. Honestly, think of this explainer as your personal mentorship session. We're going to completely demystify exactly how systems communicate over the web. Because, we build these incredible things, but none of them exist in a vacuum, right? They absolutely have to talk to each other, share data, and do it securely. By the end of our time together, you're going to have a rock-solid grasp on the building blocks that make all this internet magic actually happen. Okay, let's just quickly look at our roadmap so we keep the cognitive load light today. We're going over the API resource gateway, RESTful architectural constraints, the anatomy of a request, those four main HTTP methods, reading server responses, and finally, API authentication and security. All right, section 1, the API resource gateway, connecting systems. Before we can start building highly scalable systems, we really need to understand the foundation. So let's start with a basic definition. An API, or Application Programming Interface, is literally just the set of rules developers follow to talk to other software systems programmatically. Imagine you're building an internal timesheet app. It exposes an API that basically just says, hey, give me an employee's name and some dates. You trade that specific info, and boom, the API processes it and hands you back the exact hours worked. It's just a seamless exchange of information following a reliable standard. You can really think of a web API as a giant gateway. On one side, you've got your clients. That's us, our browsers, or other software systems. On the other side, you've got resources. That's the actual data, right? Images, text, videos, whatever is sitting on the server. So if you build a little weather app, your app is the client passing through this gateway to grab that weather data resource. But, a gateway without rules is just total chaos. And that is exactly where REST comes in. Representational state transfer. It's a software architecture that imposes very specific conditions on how an API should work to manage insanely complex networks like the internet. REST is basically the theory. It's the ultimate guideline that makes cross-platform communication actually work at scale. And when an API follows these rules, we call it a REST API. Moving on to Section 2, RESTful Architectural Constraints, Rules of Engagement. We're getting into the core theory now, where REST lays down the law. So, there are 6 main architectural constraints that make a system truly RESTful. We've got client-server separation, uniform interface, statelessness, layered system, cacheability, and code on demand. Let's look closely at the uniform interface constraint. This basically means the server always transfers info in a standard format. Even if the server internally stores data as raw, messy text, it's going to send it back through the gateway in a widely accepted format, like HTML or JSON. It completely standardizes the conversation for everyone. Now, this next one is absolutely crucial: statelessness. This is a total game changer because it completely removes server memory load. Every single time a client makes a request, the server handles it independently. It never, ever has to remember past requests. The server fulfills the request using only the info provided right then and there. Think of it like going to a busy coffee shop where the barista forgets you the second you walk away. Every time you order, you have to say exactly what you want from scratch. That's statelessness, and it's a massive reason why REST APIs scale so beautifully. And then we have cacheability. Think about visiting a website that has the exact same logo on every single page. If the server had to resend that identical image every single time you clicked a link, it would be a huge bottleneck. Instead, RESTful web services let the client store or cache these common responses. So after that first load, your browser just uses the image from its own cache, completely skipping the server interaction. It is incredibly fast. Section 3, Anatomy of a Request, Client-Server Flow. Let's shift from theory into actual implementation. What literally happens when a client pings a server? Here is a day in the life of a data request. First, the client formats and sends a request in a language the server understands. Second, the server stops and authenticates the client, basically checking their ID at the door. Third, the server processes the request internally. And finally, the server sends back a response, letting the client know how it went and handing over any requested data. Now, for that flow to actually happen, the request needs a few key pieces. It needs a URL, or unique resource identifier. This is the exact endpoint telling the server what we want. It needs an HTTP method, which we'll get to in a sec. It includes headers, which are just metadata about the request. And, my favorite, it often includes parameters. Parameters are fantastic because they let you give the server super detailed filtering instructions. You can use query parameters to ask for highly specific slices of data. All right, section 4. The 4 HTTP methods, verbs of the API.
If the URL is the noun pointing to the thing we want, these HTTP methods are the verbs.
Get is the absolute simplest action. It does exactly what it sounds like. Clients use it just to access and fetch resources from a specific URL. Because you're only reading data, GET requests are the ones that can be heavily cached. Post is your creation method. You use post when you want to send entirely new data to the server. So like when you submit a form to register a new user, you're handing that new data over within a post request for the server to process and store.
Put, on the other hand, is for modifying what's already there. Say you need to change the email address on a user profile that already exists. You'd use a put request to update that specific resource on the server.
And finally, delete. Pretty self-explanatory, right? It's used to completely wipe out a resource. Now, because this actually changes the server state in a big way, it is super powerful. And for that exact reason, a delete request will immediately fail if you don't have the strict permissions required to run it. Now, here's a classic interview question for you, junior devs. What is the real difference between post and put? Well, it all comes down to repetition. If you send the exact same post request 5 times, you'll accidentally create 5 duplicate resources. But if you send the exact same put request 5 times, it just updates the resource to the exact same state over and over. You get the same result without duplicating any records. Huge difference.
Section 5, reading server responses, understanding status. So we've sent our verbs, the server processed them, and now it's replying. We need to know how to read that reply.
Servers communicate success or failure using a 3-digit status code. A 200 code is your generic success, meaning everything went perfectly. A 201 specifically means a post method worked and a new resource was successfully created. On the flip side, a 400 means you sent a bad request that the server just can't process. And of course, the infamous 404, resource not found. Honestly, these codes are going to be your best friends for debugging. If your request was successful, along with that status code, you're going to get a message body. This contains the actual data you asked for. Depending on the headers you sent, you might get XML or a JSON payload. This plain text format, like literally name John, age 30, is exactly how the data is packaged up and handed right back to the client. Okay, final section, Section 6, API authentication and security, securing the gateway. We've built the gateway, set the rules, made requests, but now we need to lock the whole shebang down. The evolution of API security is actually pretty cool to track. Basic auth is the simplest. The client just sends a username and password encoded in base 64 right in the header. Not super secure. So then we evolved to bearer tokens. Here, the server generates a crazy encrypted string of characters after you log in, and the client just passes that token to prove they belong there. Finally, we have OAuth. This is the gold standard. It combines passwords and tokens, but gives the server the power to actually check that token over time, limit its scope, and set a hard expiration date on the access. So, there you have it. You've got the fundamental building blocks. You understand the architectural constraints, those HTTP verbs, and the security models keeping everything safe. Knowing how REST inherently optimizes things through statelessness and cacheability, I have a question for you. How are you going to apply these exact constraints to build and scale your next application? The tools are totally in your hands now. Keep building, keep learning, and I will see you in the next explainer.